Welcome back, my olfactorily observant observers. I'm your quantum-superposed astrobiologist, simultaneously excited and skeptical across infinite realities. You're tuned into the Multiverse Employee Handbook, the only podcast that treats potential alien microbial farts like the most significant scientific breakthrough since someone looked at moldy bread and thought, I should eat that. This month, in a paper published in the Astrophysical Journal, astronomers announced the detection of 2 sulfur compounds in the atmosphere of exoplanet K2-18b. On Earth, these types of molecules are primarily produced by living organisms. It's like discovering your distant neighbor's house smells suspiciously like someone's cooking, except the neighbor lives 124 light-years away, and the cooking might be alien microbes metabolizing in a global ocean. The James Webb Space Telescope's MIRI instrument has detected what might be the cosmic equivalent of microbial body odor. And for once, a bad smell might be the most exciting news in the galaxy. But before we declare aliens confirmed and start building interstellar welcome baskets, let's explore what this actually means and why astronomers are simultaneously celebrating and exercising extreme caution. Gather round the quantum conference room, my potentially populated planet pursuers, for a tale that would make even Carl Sagan double-check his evidence. In the fluorescent-lit realm of quantum improbability solutions, specifically in the astrobiology department, which existed in a superposition of underfunded research division and suddenly the most important team in the company, Dr. Anjali Piet was having what could charitably be called an extraterrestrial evidence crisis. It had started, as these things often do, with an unexpected discovery in the data. I'm telling you, the signal is there, Anjali insisted, pointing at the spectral graph displayed on the conference room screen. DMS and DMDS at 3 sigma confidence. Those are biosignature gases. The square-haired boss, whose hair maintained perfect cubic geometry despite Einstein's objections to its violation of spacetime, leaned forward, his enthusiasm inversely proportional to his understanding. Aliens! We've discovered aliens! Call the press office immediately! Wait, Anjali cautioned, raising a hand. We need to be extremely careful here. These molecules could indicate biological activity, but we need to rule out false positives first. On K2-18b, there might be non-biological processes we don't understand. Dr. Wei, the team's senior spectroscopist, nodded in agreement. The molecules are rarely produced abiotically on Earth, but K2-18b is nothing like Earth. It's a mini-Neptune, or maybe a hycean world, with a hydrogen-rich atmosphere over a potential water ocean. The square-haired boss deflated slightly, his hair losing approximately 0.3 cubic centimeters of volume. So, no aliens? We don't know yet, Anjali explained patiently. That's the point. Science doesn't work by declaration, but by progressive elimination of alternatives. We need more observations, different instruments, independent confirmation. Before Anjali could finish, the marketing director burst through the door, already clutching mock-ups of T-shirts reading K2-18b, the smell of alien life. And my boss went to K2-18b and all I got was this lousy biosignature. Too late, the marketing director announced. The press release already went out. Company scientists discover alien life. The stock is up 40%, and we've received acquisition offers from 3 major tech conglomerates and Elon Musk.
Cha-ching!
Anjali's face paled. But we haven't proven anything yet. This is terrible scientific practice. We need multiple lines of evidence, independent confirmation, peer review. The board has renamed the company tagline to Your Alien First Contact Professionals and would like to discuss movie rights, the marketing director continued, unperturbed. Also, they want a sample of the alien life by Friday. It's 124 light years away, Anjali protested. So, next Friday then? The marketing director asked hopefully. The situation deteriorated further when social media discovered the news. #AliensConfirmed and #SmellOfSpace were trending worldwide. 3 religions had already incorporated K2-18b into their cosmology, and a cryptocurrency called Alien Coin had reached a market cap of $2.3 billion, despite having no actual function.
Wait, what?
Anjali sat in her office, watching the scientific process being trampled by excitement, and contemplated her options. The data was real, the detection was significant, but the interpretation required extreme caution. How could she communicate both the legitimate excitement and necessary skepticism to a world that wanted simple answers? That's when Dr. Wei appeared at her door. "I've been thinking," he said. "Why don't we invite independent teams to analyze our data and propose follow-up observations that could either strengthen or weaken the biosignature hypothesis?" "And what about the media frenzy?" Anjali asked. "Science is self-correcting in the long run," Wei replied with a small smile. "Our job is to follow the evidence wherever it leads. If it's not life, that's still an important discovery about abiotic chemistry on exoplanets. If it is life..." He paused, allowing himself a moment of wonder. "Then we've answered one of humanity's oldest questions." Anjali nodded and turned to her computer. "Let's draft the follow-up research proposals. The truth, whatever it is worth getting right." And that, dear listeners, brings us to the fascinating science behind these potential biosignatures and why even a stinky sulfur compound might be the most exciting discovery in decades. And that brings us to the science of K2-18b and its potentially biologically produced stench.
Gross.
Unlike the square-haired boss's premature conclusion, this discovery represents not an endpoint, but the beginning of a long scientific journey. First, let's understand what was actually found. The James Webb Space Telescope's mid-infrared instrument, MIRI, detected spectral signatures that are best explained by the presence of dimethyl sulfide, DMS, and/or dimethyl disulfide, DMDS, in the atmosphere of K2-18b. These sulfur compounds have a characteristic spectral fingerprint between 6 to 12 micrometers in wavelength. On Earth, these molecules are almost exclusively produced by living organisms, particularly marine microbes. Phytoplankton in our oceans release approximately 200 million tons of DMS annually, accounting for about 90% of all the DMS in Earth's atmosphere. DMDS is similarly biological in origin, often resulting from the breakdown of organic matter. If you've smelled rotting cabbage or certain strong cheeses, you're familiar with DMDS. The detection itself is statistically significant at about 3 sigma confidence. In scientific terms, this means there's approximately a 99.7% chance that the signal is real and not just random noise. A statistical threshold remarkably similar to the probability that any attempt to explain this finding at a family dinner will result in your uncle asking if aliens built the pyramids.
Yup.
However, establishing that these molecules are actually present is only the first step. The far greater challenge is determining whether they are produced by living organisms or by some as yet undiscovered abiotic process unique to K2-18b's alien environment. Previous observations of K2-18b had already detected methane and carbon dioxide in its atmosphere while finding no evidence of ammonia, a composition consistent with a hycean world, a planet with a hydrogen-rich atmosphere above a potential water ocean. With the addition of these potential biosignature gases, the case for K2-18b as a habitable and possibly inhabited world becomes more intriguing. When we return after this break, we'll dive deeper into K2-18b itself, the significance of these smelly molecules, and why astronomers are both excited and extraordinarily cautious about claiming evidence of extraterrestrial life. Welcome back, my spectrally sleuthing space scientists. While you were away, our automated response system analyzed 47 different abiotic mechanisms that could potentially produce DMS or DMDS without biological assistance. Its conclusion? Insufficient data. Recommend against both premature celebration and dismissal. Even our AI knows better than to jump to conclusions about alien life. Let's dig deeper into K2-18b itself. Located approximately 124 light-years away in the constellation Leo, it orbits a cool red dwarf star called K2-18. The planet has a mass about 8.6 times that of Earth and a radius 2.6 times larger, putting it firmly in the category of sub-Neptunes, the most common type of planet in our galaxy that doesn't exist in our solar system at all. K2-18b orbits within its star's habitable zone, where temperatures could permit liquid water to exist on a surface. However, with a planet this size, scientists initially weren't sure about its nature. Is it a mini Neptune with a deep hydrogen atmosphere and no solid surface? A gas dwarf with a rocky core and thick atmosphere? Or perhaps a hycean world, a hybrid planet with a water ocean beneath a hydrogen-rich atmosphere? Previous JWST observations in 2023 detected significant amounts of methane and carbon dioxide in its atmosphere, along with a conspicuous absence of ammonia. This composition strongly suggests K2-18b is not a mini Neptune with a deep hydrogen envelope, but more likely a hycean world. The latest observations detecting potential biosignatures DMS and DMDS add another fascinating piece to this planetary puzzle. The discovery was made using JWST's mid-infrared instrument, MIRI, which observed the planet's atmosphere as it transited its star. Unlike previous observations in the near-infrared range, 1 to 5 micrometers, these observations captured longer wavelengths, 6 to 12 micrometers, where DMS and DMDS have strong absorption features. Essentially, these molecules leave their unique fingerprints on the starlight, passing through the planet's atmosphere. What makes this detection particularly interesting is the strength of the signal. The researchers found that DMS and/or DMDS must be present at relatively high abundances, approximately 10 parts per million. On Earth, DMS exists at around just 1 part per billion in our atmosphere. But why are these specific molecules so important as potential biosignatures? DMS and DMDS are considered robust biosignatures because they're difficult to produce without biological processes, particularly in a hydrogen-rich atmosphere. On Earth, DMS is primarily produced by marine phytoplankton as a byproduct of their metabolism. When these microorganisms are stressed or die, they release dimethyl sulfonylpropionate, DMSP, which breaks down into DMS. The researchers considered 20 different molecules that could potentially explain the observed spectral features, including various hydrocarbons and sulfur compounds. Their analysis showed that only DMS and DMDS could adequately account for the observations. This wasn't just a case of scientists finding what they were looking for. These molecules emerged as the best explanation after testing numerous alternatives. But, and this is the critical scientific caveat, just because these molecules are biologically produced on Earth doesn't necessarily mean they're produced by life on K2-18b. The planet's alien environment could host unknown abiotic chemical pathways that produce these compounds without requiring biology. As Carl Sagan wisely noted, extraordinary claims require extraordinary evidence, and the claim of detecting extraterrestrial life would be among the most extraordinary in scientific history. So where do we go from here? If there's one thing scientists love more than making discoveries, it's methodically testing those discoveries until they're absolutely certain, or until they find something even more interesting to test. The first step is independent confirmation. While the detection of DMS and DMDS is statistically significant at about 3 sigma, scientists typically require a 5 sigma detection, 99.9999% confidence, for extraordinary claims. Additionally, the current observations show a degeneracy between DMS and DMDS, meaning both molecules have similar spectral features in this wavelength range, making it difficult to definitively distinguish between them. Future observations with different JWST instruments could help resolve this degeneracy and increase the confidence of the detection. The researchers estimate that with just 1 to 3 additional transits observed with MIRI, they could increase the detection significance to 4 to 5 sigma. That's just 8 to 24 more hours of precious JWST observation time. Beyond confirming the presence of these molecules, researchers need to thoroughly investigate every possible non-biological explanation. Laboratory experiments and theoretical modeling could explore whether conditions unique to K2-18b might enable abiotic production of DMS and DMDS. For example, experiments could test whether UV radiation interacting with methane and hydrogen sulfide in a hydrogen-rich atmosphere could produce these compounds. In science, it's not enough to have evidence of life. You must also thoroughly disprove all non-life explanations. The authors of the study point out another important limitation. Our understanding of these molecules' spectral properties is based on Earth conditions. The absorption properties of DMS and DMDS might differ in the hydrogen-rich, low-pressure environment of K2-18b's upper atmosphere. New laboratory measurements and theoretical calculations are needed to ensure we're interpreting the spectral data correctly. Perhaps most importantly, scientists would want to detect multiple mutually supporting biosignatures. Finding one potential biosignature is intriguing. Finding several that form a consistent biological picture would be far more convincing. On Earth, life maintains our atmosphere in a state of chemical disequilibrium. For example, oxygen and methane coexist despite their tendency to react and destroy each other. Similar disequilibrium on K2-18b would strengthen the biological hypothesis. We also need to better understand the planet itself. Is there actually a liquid water ocean under that hydrogen-rich atmosphere? What's the planet's true surface temperature? Is it hot enough to melt lead or cool enough for liquid water? The habitability question must be answered definitively before we can seriously consider the inhabited question. Where does this leave us? The detection of DMS and DMDS in K2-18b's atmosphere is a genuinely exciting discovery that opens new avenues for exoplanet science and astrobiology. It represents the first detection of potential biosignatures in the atmosphere of a habitable zone exoplanet. a significant milestone regardless of whether these molecules ultimately prove to be biologically produced. But we must be patient. The journey from interesting spectral features to evidence of extraterrestrial life is long, methodical, and filled with necessary skepticism. Each step forward must be tested, verified, and challenged. This is not a weakness of science, but its greatest strength. The self-correcting process that gradually brings us closer to truth. As astronomer Carl Sagan wisely observed, somewhere something incredible is waiting to be known. K2-18b may be giving us our first whiff of that incredible something, or teaching us about previously unknown abiotic chemistry. Either outcome represents a profound advancement in our understanding of the universe and our place within it. Well, my biosignal-sniffing stargazers, we've reached the end of another cosmic conundrum. Today we've learned that in the multiverse of potential extraterrestrial habitats, every planet exists in a superposition of possibly inhabited and probably sterile, until significant scientific evidence collapses the wave function. We've discovered that even a whiff of alien body odor, in the form of dimethyl sulfide and dimethyl disulfide, is enough to send both the astronomical community and podcast hosts into careful, measured, scientifically appropriate excitement. Though I suspect somewhere in the vast expanse of the cosmos, microbial life might be equally fascinated by the peculiar spectral signatures of human civilization, particularly our suspicious production of reality television and processed cheese. The detection of potential biosignatures represents a watershed moment in astrobiology, regardless of the final outcome. If further research confirms a biological origin for these sulfur compounds, we will have answered one of humanity's oldest questions. Are we alone in the universe? If instead, we discover novel abiotic pathways that can produce these molecules without life, we'll have expanded our understanding of planetary chemistry in ways that will inform future biosignature searches. Either way, the proper scientific approach remains the same: careful observation, independent verification, thorough consideration of alternative explanations, and a healthy dose of both excitement and skepticism. Science progresses not through dramatic declarations, but through the steady accumulation of evidence and the elimination of alternatives. A process that can sometimes feel frustratingly slow, but ultimately leads to genuine understanding. And somewhere out there, through the vast expanse of space and time, K2-18b continues its orbit around its red dwarf star, completely indifferent to our excited speculations about what might be swimming in its possible oceans. Whether it hosts a thriving biosphere or is merely an interesting case of exotic chemistry, it has already achieved something remarkable. It has reminded us that the universe is often stranger, more complex, and more fascinating than we can imagine. And if you've enjoyed our aromatic adventure through the potential alien biosphere of K2-18b, why not share this episode with a friend who might appreciate knowing their gym socks smell vaguely similar to humanity's first potential detection of extraterrestrial life? Follow us on Threads, where we regularly post updates and respond to your questions about the cosmos and corporate absurdity. This is your quantum coherent correspondent, reminding you that in the grand cosmic search for life, we're all just following our noses, one spectral line at a time.
The Multiverse Employee Handbook was created by Rob Corrigan. The host, David, is a professional voice actor who has digitized his voice through 11 Labs voice cloning technology. All episode thumbnails are created with OpenAI, and music and sound effects come from Pixabay, which are generated by human artists, not AI. Everything else, the writing, jokes, research, sound editing, and coffee consumption, is 100% human-made by a human. No cats are harmed in the making of this podcast. Visit our website for more information about the Multiverse Employee Handbook.